In exactly 2 days, something amazing will happen. An object from beyond our solar system, traveling at 137,000 miles per hour, will fly just 18 million miles from us, and we will capture it for the first time with unprecedented resolution. But this is where the strangest part begins. This object weighs 33 billion tons, which is 3 to 5 times heavier than any interstellar object we have ever discovered. It has no tail, yet it ejects 150 kilograms of material into space every second. The glow is directed forward, not backward. It emits nickel without iron, violating fundamental laws of chemistry, and its trajectory perfectly aligns with the plane of our solar system, which has a statistical improbability of only 0.2% for natural origin. Aviva Loba from Harvard, the scientist who studied Oumuamua, rated this object 6 out of 10 for artificial technology. Meanwhile, NASA has just published peer-reviewed evidence of possible ancient life in stones with a spotted leopard pattern on Mars. That week, HSBC became the first bank to apply quantum computing in real trading, outperforming classical computers by 34%. GPT-5 was launched, and users rebelled, claiming it had become lobotomized. France maintained nuclear fusion for 22 consecutive minutes, and China's carbon emissions decreased for the first time in history. It is October 2025, and science is advancing so rapidly that yesterday's breakthroughs are already outdated news. In the next 2 hours, we will connect all the facts, from the interstellar anomaly passing Mars in 48 hours to life found by NASA in ancient Martian soil, from quantum computers hitting Wall Street to artificial intelligence perceived as soulless, from the resurrection of extinct 12-foot birds to medical miracles curing diseases once deemed incurable. Some of these stories were ignored by the mainstream media, others were covered without understanding their significance, and some are actively trying to avoid mentioning. These are scientific news that they do not want you to connect. It is October 2025, and events are becoming very, very interesting. If you are ready to dive into this topic, press the like button and subscribe. Then write in the comments where you are listening from, what time it is for you, and what strange things have ever happened to you. Let's begin. Chapter 1. 3-Eye Atlas, linking the facts of the anomaly. So, the 3-Eye Atlas is now less than 48 hours from its closest approach to Mars. You have been following this story. You know about the light directed forward that should not exist. Are you aware of Loeb's works showing incredibly high masses? You've seen speculations and refutations, counter-refutations, but what you may not have connected is what will happen on October 3rd when several spacecraft simultaneously point their cameras at this object. The Martian Reconnaissance Orbital Spacecraft, China's Tianwen-1, as well as Mars Express, and the HO Orbiter are all coordinated to capture images with a resolution we've never had before, 30 kilometers per pixel. This may not sound impressive until you realize what it means. For the first time, we will be able to separate the core of this object from the surrounding cloud of dust. We will see its true shape, surface features, and determine whether it rotates chaotically or in a controlled manner. And this is what makes this moment so unusual. The teams working on these orbiters did not plan to conduct such observations. The Mars orbiters are intended to study the planet itself, not to photograph objects millions of kilometers away in space. But when the scientific community realized that Tri-Eye Atlas would pass so close that planetary probes could capture it clearly, a rush began. Observation schedules were rewritten, and the operating time of instruments, which usually takes months, was reassessed in just a few days. Why such haste? Because such an opportunity comes only once. Tri-Eye Atlas moves at interstellar speeds. After passing Mars, it will continue towards the Sun, reaching perihelion on October 29th. Then he will disappear, thrown back into space by the Sun's gravity, slipping away from us forever. We have only one chance, one window of time, and this window will open in 2 days. Now is the time for the final data. 6 days ago, Avi Loeb's colleagues published a new article, not a preliminary version or a blog post, but a peer-reviewed analysis that passed all stages of scientific scrutiny, and what was revealed in it completely changed the course of the discussion. The article analyzed over 4,000 observations of the Tri-Eye Atlas, collected by 227 observatories worldwide from May 15th to September 23rd. They were searching for something specific: non-gravitational acceleration. When a comet approaches the Sun, the ice on its surface turns directly from solid to gas, a process called sublimation. This gas emission acts like tiny rocket engines, slightly shifting the comet from its gravitational trajectory. Every active comet we have ever studied demonstrates this effect. However, 3I Atlas shows no detectable non-gravitational acceleration. None. Let that sink in. The Hubble telescope confirmed that this object is losing 150 kilograms of mass every second, which is 330 pounds of material ejected into space each second at a speed of 440 meters per second, nearly 1,000 miles per hour. This is no subtle effect. It is a powerful, continuous rocket thrust that has been ongoing for several months. Yet, when you construct the trajectory of the 3I Atlas with high precision, using thousands of observations, it strictly follows a gravitational path. The residual acceleration, deviation from what is predicted by gravity alone, is less than 15 meters per day squared. In comparison, this is about 100,000th of Earth's gravitational acceleration, effectively zero. How is it possible to maintain a continuous rocket thrust of such magnitude and hardly notice the acceleration? The answer can only be one. The object must be absurdly massive, so massive that the thrust, although colossal in absolute terms, becomes insignificant compared to the object's inertia. The calculations are quite simple. Considering the observed mass loss rate and material ejection speed, the absence of measurable acceleration indicates a minimum mass of 33 billion tons. 33 billion tons. This gives a minimum diameter of 5 kilometers, assuming solid density. 5 kilometers is not 20 kilometers. It's less than earlier estimates based on brightness, but still, it's a huge figure. It is still at the limit of the size range allowed by Hubble's observations, and it is still 3 to 5 times more massive than Oumuamua. Now the question arises, for which no one has a good answer. Where do 33 billion tons of interstellar objects come from? The reserves of heavy elements in interstellar space are limited. The rocky materials that make up planets and asteroids must be ejected from planetary systems. Planets form around stars. As these planetary systems evolve, some material is ejected into interstellar space through gravitational interactions. This is where Oumuamua came from, and also where the two comets E.I. Borisov originated. This is the reservoir from which we draw. But this reservoir has a distribution by size. Small objects are common, while large ones are rare. Exponentially rare. Statistical calculations show that an interstellar mass supply could deliver a 20-kilometer diameter asteroid to the inner solar system approximately once every 10,000 years. Even if we try to pack all available interstellar rocky materials into pieces of 20 kilometers, which seems absurdly optimistic, it will still happen once every 10,000 years. We are seriously searching for interstellar objects less than 10 years old, and have found only one. The likelihood that this happened by chance is extremely low. It resembles buying a lottery ticket and winning the jackpot on the first try. Even less so. Here, we should consider unpleasant possibilities, unless the assumed distribution of sizes is incorrect. If there exists a population of massive interstellar objects that do not conform to the statistical rules derived from the study of our solar system, if 3I Atlas are not a random piece of ice and rock that just wandered into our system, if it is something else, Leib rated this a 6 on his scale. 6 out of 10. He created this scale specifically for such situations. 0 means it's definitely a natural phenomenon. 10 means it's definitely technological. 6 means that the evidence is convincing enough to dismiss the possibility of ignoring it, but not enough to reject natural explanations. 6 means we need more data, and in 2 days, we will get that data. A high-resolution camera on Mars orbital surveying will capture images. If the core is more than 5 kilometers, and the brightness we observe primarily comes from a solid object rather than a dust cloud, then the natural explanation becomes untenable. It's just impossible to pack such a mass into interstellar space and discover it on the third attempt. Statistics break down. The model collapses. But if the nucleus is small, and most of the brightness comes from the sparse coma of gas and dust surrounding the relatively modest nucleus, then we are dealing with an unusual, yet ultimately natural cometary object. Strange, yes. Anomalous in its chemistry and absence of a visible tail, but explainable within the known laws of physics. 2 results, 2 completely different conclusions, and the answer will be known on the 3rd of October. Now let's talk about chemistry, because this is where things really get strange. Multiple spectroscopic observations confirm that the three-eyed atlas emits nickel, not iron, nickel. In every natural astronomical object we have ever studied, nickel and iron go hand in hand. They are chemically similar, form under similar conditions, and when you see one in the spectrum, you see the other. The ratio varies, but both are always present. The three instruments show nickel without iron. The spectrum is clear and unambiguous. Nickel lines are present. There are no iron lines. This is not a case where iron is present but below the detection limit. The instruments are sensitive enough. If iron were in the expected ratios, we would have seen it. We do not see it. There is no good natural explanation for this. It is impossible to deliberately form nickel without iron in any synthesis process in the core of a star that we know. It is chemically impossible to separate them after formation, as they behave almost identically. It is impossible to selectively deplete one element through sublimation or any other superficial process, as they sublimate at similar temperatures. Chemistry does not work. And yet, here it is. Nickel without iron, a sign that should not exist, stubbornly persisting in observations. Then there is a trajectory. Have you heard of the alignment along the ecliptic that three Atlas satellites move almost perfectly in the plane of the solar system's planets? The probability is 0.2%. Rare, but not impossible. Unusual coincidences occur, but the trajectory has other properties that accumulate one coincidence after another. The orbit brings three unusual Atlas moons remarkably close to Venus, Mars, and Jupiter. Not to the nearest approach to Earth, but closer than a random interstellar trajectory should allow. The minimum distance of the orbit intersection with Mars, the closest point of the path of 3 Icarus, is only 2,700,000 kilometers, which is about 7 times the distance from the Earth to the Moon. For an object coming from interstellar space on a trajectory set millions or billions of years ago, passing so close to the planet's orbit is a precise adjustment. Gather all of this together: mass, chemistry, trajectory, absence of non-gravitational acceleration despite active gas emission, glowing in front instead of a tail, and each of these phenomena seems strange on its own. Some have potential explanations, although they often require special circumstances or unusual conditions. But when all these anomalies converge in one object, it raises serious questions. This is exactly what Loeb means when he gives a score of 6. Not that each individual anomaly is conclusive, but that the accumulation of anomalies, the gathering of statistically unlikely and physically strange occurrences in one object, reaches a level that demands serious consideration of alternatives. And so we wait. 48 hours. The most advanced camera of humanity is aimed at another planet, capturing an object beyond our solar system, catching photons that will tell us whether we are looking at the rarest natural comet ever found or something that completely defies natural explanation. October 3rd, 2025. In any case, we are going to learn something profound about our place in the universe. Chapter 2. Life on Mars. Speckled stones. While the world watches the three-eyed Atlas approach Mars, something equally unusual has been sealed in a tube on the surface of Mars for over a year, and 3 weeks ago, it finally passed the strictest scientific review. On September 10th, 2025, the journal Nature published an article that NASA had kept secret, analyzing, discussing, and scrutinizing for 14 months. The article describes a rock sample collected by the Perseverance rover in July 2024, nicknamed Sapphire Canyon, highlighting its unique content and potential significance. The rock formation has an official name, Chayava Falls, named after a waterfall in the Grand Canyon, following the mission's tradition of borrowing names from earthly objects. Perseverance stumbled upon it while exploring an area known as the Formation of the Bright Angel, a set of rocky outcrops at the edge of the Neretva Valley. The Neretva Valley is an ancient river valley carved billions of years ago, when water forcefully rushed into the Azer crater, capable of moving boulders the size of cars. When the rover's camera first captured an image of Chayava Falls, the scientific team noticed something unusual. The surface of the rock was covered with spots, not random dents or signs of erosion, but spots with distinct leopard-like patterns and colors ranging from light white to deep black, with flecks of green and blue. On Earth, such patterns form under very specific conditions, where chemistry and biology intersect. The rover has 2 tools perfectly suited for this kind of research: Pixel, a planetary instrument for X-ray lithochemistry, and Sherlock, which investigates habitable environments using Raman spectroscopy and luminescence to search for organic compounds and chemicals. Yes, he was indeed named Sherlock. Scientists have a sense of humor. These instruments can analyze the chemical composition of rocks at a microscopic level without making holes in them. They can identify minerals, detect organic compounds, and map the distribution of various chemicals on the surface. What they found at Cheyava Falls resembles a recipe for ancient microbial life. First, it is fine-grained alurite. Aluvrites form on Earth in calm aquatic environments, on lake bottoms, in river deltas, places where sediments slowly settle from still water. This fully aligns with what we know about the history of Lake Crete. 3.5 billion years ago, there was a lake here, fed by rivers that cut through the edge of the crater, depositing sediments in layers that eventually turned to stone. The fine-grained alurites preserve biological signatures excellently. Tiny particles are densely packed, creating a matrix that can capture and protect organic molecules for billions of years. If microbial life existed in that ancient Martian lake, it is in the alurites that we would hope to find its traces. Secondly, the chemical composition. The instruments detected oxidized iron, rust, and not just traces, but a significant amount. They also found phosphorus, an element essential for life as we know it. It is a key component of DNA, RNA, and adenosine triphosphate, a molecule that stores and transmits energy in living cells. Sulfur was also found in several chemical forms, as well as organic carbon molecules. The term organic does not always mean biological. Organic molecules can form through purely chemical processes. Meteorites contain organic compounds, as do interstellar clouds, but organic carbon in the context of alurites, phosphorus, sulfur, and iron significantly narrows the possibilities. The distribution of substances is also important. The leopard spots are not uniform. The chemical map showed that the spots contain specific minerals, vivianite and greigite. These are iron phosphate and iron sulfide minerals, respectively. Vivianite and greigite form on Earth at low temperatures through a process called the redox cycle, where reduction and oxidation reactions occur. A key point is that the most common way to obtain an active redox cycle in mud deposits on Earth is through microbial activity. Think of it this way. Microorganisms need energy. They obtain it by moving electrons. On Earth, many microorganisms living in sediments consume organic matter and use oxidized iron or sulfate as electron acceptors. They breathe rust just as we breathe oxygen. When this happens, they alter the local chemistry, creating microenvironments with various oxidative states. Over time, these chemical gradients settle as different minerals. Minerals form patterns that reflect the metabolic activity of microbial communities. Leopard spots at Cheyava Falls demonstrate this type of patterning. Small areas the size of a millimeter, where vivianite and greigite are concentrated, are surrounded by slightly different mineral associations. This spatial organization is associated with biological activity on Earth. However, and this is important, we cannot confidently assert that biology is the only explanation. That is why the article uses the term potential biosignature. A biosignature is evidence that may indicate the presence of life in the past or present. The word potential emphasizes that we need more data before drawing final conclusions. There are alternative explanations, though they are less likely considering the full picture. One of them is that all of this could have occurred purely due to abiotic chemistry. High-temperature events, possibly caused by volcanic activity or meteorite impacts, could have created some of these minerals. However, the team analyzed the texture and crystalline structure of the rocks. There is no evidence of heating. Minerals formed at low temperatures in cold water. Excluding high-temperature processes significantly reduces biotic options. Another alternative is a detailed sequence of events. Perhaps organic molecules arrived from space, delivered by meteorites or interplanetary dust. Perhaps iron minerals formed from the circulation of underground waters after the lake had dried up. Maybe the spatial patterns are random. Perhaps each piece of the puzzle has a separate, unrelated explanation. This is possible, but it requires assuming multiple independent processes that just coincided in the same rock. Occam's razor principle, stating that simpler explanations are usually more likely, begins to lean towards biology, though not definitively. But it was enough for the scientific team, after a year of analysis and discussions, to confidently call it a potential biosignature, and published the results in one of the most prestigious scientific journals. Joel Harrowit from Stony Brook University, the lead author of the article, expressed himself cautiously. The combination of chemical compounds found in the bright angel formation could be a rich source of energy for microbial metabolism. But just because we saw all these convincing chemical signatures in the data, it didn't mean we had a potential biosignature. We needed to analyze what these data might mean. This cautious approach is important. Scientific work at this level does not involve hasty conclusions. It is weighing evidence, considering alternatives, and honestly reporting uncertainty. The team says, here is what we found, here is what it might mean, here is what we still need to figure out. And this last part, what we still need to figure out, is the source of frustration because the Sapphire Canyon is sealed in a tube on Mars. The rover's tools are good. These are incredibly complex engineering devices, but they are limited in size, weight, and energy resources. They cannot perform isotopic analysis. They cannot conduct high-resolution electron microscopy. They cannot carry out dozens of tests available in laboratories on Earth. To truly determine whether the leopard spots in the Sapphire Canyon are biological or abiotic, we need to bring it back to Earth. We must deliver it to the laboratories, where we can subject it to all available analytical methods, where we can compare it directly with samples from Earth, where we can confidently rule out alternative explanations, rather than just speculate. The return of samples from Mars was planned from the very beginning. Perseverance is not just exploring Mars, it is collecting samples specifically chosen for their scientific value and sealing them in tubes designed to maintain ideal conditions during the journey back to Earth. At this point, the rover had collected 30 samples, and the Sapphire Canyon was among them. The mission's architecture involved collaboration between NASA and ESA on a complex sequence. A special rover would collect samples from Perseverance or from deposits on the surface. A rocket for ascending to Mars would launch them into orbit, and an orbital craft for returning to Earth would capture them and bring them home. On Earth, sample storage facilities would receive them under strict contamination prevention protocols. This was the plan, but now the return of samples from Mars is at risk. Budget overruns, technical difficulties, political pressure. The cost of the mission has significantly increased compared to initial estimates. Congress has begun asking tough questions. NASA began seeking alternatives, simplified architectures, partnerships with commercial space companies, all to reduce costs and complexity. But even optimistic new timelines pushed the return of samples to the 2030s. Pessimistic scenarios suggest that this may never happen at all. Thus, the Sapphire Canyon remains on Mars, the most enticing potential evidence of life beyond Earth, sealed in a tube, and waiting. The scientific team published their results because peer review and publication are the foundation of the scientific process. You make your data available, allow the community to evaluate your findings, and open yourself to criticism and alternative interpretations. This is the process that makes science reliable. But the article ends with something like a plea. We did everything we could with the rover. The next steps require laboratory analysis on Earth, meaning that the return of samples must be prioritized and funded, not as a distant possibility. Katie Stack Morgan, the project scientist for Perseverance at JPL, expressed this accurately. Astrobiological claims, especially regarding the potential discovery of past extraterrestrial life, require compelling evidence. The discovery of a significant finding, such as a potential biosignature on Mars in a peer-reviewed publication, is an important step in the scientific process as it ensures the rigor, validity, and significance of our results. Although abiotic explanations for what we observe at Bright Angel are less likely considering the conclusions of the article, we cannot exclude them. Less likely, but not impossible. And this cannot be dismissed. This is a candid expression of science facing the limits of remote research. We have reached the limits of robotics and remote sensing. The next step requires samples. Meanwhile, the Perseverance rover continues its research, exploring other areas of Jezero crater in search of additional rocks like Cheva Falls. The formation of Bright Angel is not unique. It is part of a broader geological context. Layers of sedimentary rock that capture various episodes of Mars' watery past. Each rock tells its part of the story. Some of them are more altered, indicating extensive interaction of water with rock formations. Others are more pristine, preserving older mineralogy. Studying this diversity, the mission forms a complete picture of how the Jezero crater has evolved over time. The latest analysis, published just a few days ago, further expanded this understanding. Using high-resolution geochemical data from several sites, researchers identified 24 different types of minerals in the crater. These are not only attention-grabbing minerals like vivianite and greigit, but a whole set of minerals revealing a dynamic history. Minerals forming in acidic conditions, minerals forming in alkaline conditions, minerals requiring water, minerals indicating desiccation. As a result, a story of multiple episodes emerged. Mars was not initially wet, then dry. It was wet, then dry, then wet again, and dry once more. The chemistry changed. The early liquids were acidic, hostile to most forms of life we know. Later, the liquids became more alkaline, more neutral, more favorable. The leopard spots in Shiva Falls formed during one of these more favorable periods. A time when, if microbial life could take hold anywhere on Mars, the Jezero crater would be the ideal place for its existence. This is why astrobiology is so complex. It's not enough to simply find organic molecules. It's not enough to discover minerals associated with water. The right combination at the right time and under suitable conditions is necessary. It must be preserved for billions of years. Luck is needed when choosing the landing site for your rover. Even then, when everything aligns, you receive potential biosignatures, perhaps probabilities, evidence that sparks interest but does not yet convince. Nevertheless, despite reservations and uncertainties, as well as the disappointing wait for the return of samples, September 10th, 2025, will be remembered. This is the day when the scientific community officially recognized, through a rigorous peer review process, that we found something on Mars that could be evidence of ancient life. This is not a false alarm, not a retracted statement, not a misinterpretation that later fell apart, but a legitimate, thoroughly analyzed, comprehensively verified potential biosignature. The article will be discussed. Alternative explanations will be proposed and tested. Some scientists will remain skeptical until the return of samples provides definitive answers. Others will see the preponderance of evidence as already convincing. Such is the nature of science. It is messy, uncertain, slow. However, it is the most reliable way to understand reality. The reality we face is this: Mars, this cold, dry, deathly-looking planet in the night sky, may not have always been lifeless. 3.5 billion years ago, when Earth was a young planet just beginning its biological experiments, Mars might have been doing the same. Two planets, two stories of the origin of life, separated by millions of kilometers of cosmic space, yet sharing the same cosmic moment of possibilities. Chapter 3. Quantum computing becomes a reality. On September 24th, 2025, an event occurred that most people overlooked. Financial publications reported on it. Technical publications covered the event. But the general public, focused on interstellar visitors and Martian microorganisms, hardly noticed. It's a shame, because what happened that day could have been the moment when quantum computing ceased to be a laboratory curiosity and became a real technology impacting the world. HSBC, one of the largest banks in the world, announced that it has used a quantum computer to solve a real business problem better than classical computers could. Not a demonstration, not a conceptual proof, not a carefully crafted situation created to showcase the advantages of quantum computing. A real problem: bond trading, predicting whether a deal will be executed at the specified price. The quantum approach provided a 34% improvement over standard classical methods. In finance, where algorithms are already hyper-optimized and every fraction of a percent matters, this is not just a step forward, it's a transformation. This is what makes it significant. For decades, quantum computing has been a technology that has always been 10 years ahead. Researchers have demonstrated impressive results in laboratories under carefully controlled conditions. Companies announced roadmaps promising practical quantum computers in the near future. Investors poured billions into quantum technology startups. But when it came to the actual use of quantum computers to solve problems important to businesses or governments, or anyone outside the quantum computing community, progress was extremely slow. The issue was not that quantum computers didn't work. They worked. Researchers could create quantum states, manipulate qubits, and execute quantum algorithms. The problem was that quantum computers were fragile, error-prone, and useful only for very specific types of tasks. For most real tasks, a good classic computer with optimized software was faster, cheaper, and more reliable. This created a chicken and egg dilemma. Quantum computers needed real use cases to justify further investment. But real examples of use required quantum computers that were stable and powerful enough to be beneficial. HSBC and IBM have just broken this cycle. The problem they solved lies at the heart of over-the-counter bond trading. When a client requests a quote for a corporate bond, the bank must assess the likelihood that the deal will be made at the specified price. It depends on the current market conditions, specific characteristics of the bond, the volume of the transaction, competing offers from other institutions, and many other factors. If the assessment is correct, the bank makes a profit. If not, he either loses the deal to a competitor or concludes it under unfavorable conditions. For this, banks use complex algorithms, statistical models, machine learning, classical optimization methods. These methods are effective, but not perfect. The problem space is vast. Variables interact nonlinearly, and there is a compromise between speed and accuracy. Classical algorithms make approximations since exact computations would take too much time. Quantum computers solve certain optimization problems differently. Instead of sequentially exploring the solution space, they can simultaneously consider multiple options thanks to quantum superposition. Instead of getting stuck in local optima, they can use quantum tunneling to escape such situations. For problems with suitable mathematical structures, quantum methods can find better solutions faster. The HSBC trial used IBM's Heron quantum processor. Heron is the last and most powerful quantum chip from IBM. It has a relatively modest number of qubits compared to some experimental systems, but the quality of the qubits, error rates, coherence time, and operation accuracy are what matter. Heron achieves over 99% accuracy in operations with 2 qubits, which is the threshold after which quantum error correction becomes possible. The team used historical trade data. More than 1 million requests for quotes on 5,000 corporate bonds from September 2023 to October 2024. Real data, real market conditions, real complexity. They developed a quantum algorithm that encoded the probability assessment task into a form that Heron could process. Then they ran it. The quantum model, combining quantum processing with classical machine learning methods, surpassed purely classical approaches in prediction accuracy by 34%. This figure is not taken from a single selected example. This is the average value across various market conditions, different types of bonds, and changing transaction volumes. Philip Interlura, head of HSBC's Quantum Technology Group, called it a breakthrough. This is a vivid example of how modern quantum computers can solve real business problems on a large scale and provide a competitive advantage that will only grow as quantum technologies advance. We are tirelessly focused on the short-term applications of quantum technologies, and since the test yielded positive results on current quantum equipment, we are confident that we are on the brink of a new era in computing and financial services. The phrase, "on the brink," is significant. If HSBC managed to gain a 34% advantage in bond trading using quantum computers, what will happen when their competitors start using the same technology? What will happen when this advantage spreads to other types of trade, portfolio optimization, risk assessment, and fraud detection? As Meklos from McKinsey put it directly, if one bank starts using quantum computing to develop a program, the others will begin working on it the next day, and no one will sleep until they acquire similar technology. This is an arms race, but not the one we usually worry about. It's a race of calculations. Whoever possesses the best quantum algorithms, the most stable quantum equipment, and the smartest analysts trained in quantum technologies gains the advantage. In the financial sphere, any advantage accumulates. Small advantages turn into large profits. Large profits finance further development. In a few years, quantum computing may become as essential for competitive banking as high-frequency trading infrastructures are today, and finance is just the beginning. In the same week that HSBC made the announcement, researchers from the University of New South Wales published results showing that silicon quantum chips can maintain 99% accuracy even when produced in standard semiconductor factories, not in specialized laboratories with individual processes, but in the same enterprises that manufacture ordinary computer chips. This is the breakthrough in scalability that the industry has been waiting for. The Dirac startup, commercializing this technology, demonstrated that exotic materials or extreme customization are not needed. Silicon qubits, controlled by the same methods as classical transistors, can achieve the necessary quality indicators for error-resistant quantum computations. And since they are made of silicon using existing manufacturing infrastructure, they can potentially be produced on a large scale. Imagine quantum coprocessors in data centers. They do not replace classical central processors, but complement them, performing specific computational tasks where quantum approaches excel, while classical processors handle everything else. Hybrid classical and quantum systems work together seamlessly. This is a vision of IBM's quantum-centric supercomputing, just demonstrated by HSBC. Now, about Google. On September 12th, researchers using a Google quantum processor with 58 qubits created something that existed only in theoretical articles, a fractionally topologically ordered state. This phase of matter cannot exist in equilibrium. It requires constant influence, periodic disturbances that keep the system in a state where it never settles naturally. Think of it as juggling. The balls in the air are not in balance. Gravity seeks to pull them together. But if you keep the system going by throwing balls in the right rhythm, you maintain a pattern that disrupts the laws of equilibrium. Fractionally topological states are thought to have properties useful for quantum computing: protection against certain types of errors, new methods of encoding information, the ability to perform quantum operations that are difficult or impossible to achieve in equilibrium systems, the creation of a real quantum processor, observing its properties, confirming the correspondence between theory and experiment. This is the foundation of science that underpins future technologies. At Kyoto University, researchers solved a problem that had troubled scientists for 10 years in the field of quantum entanglement, specifically regarding W states, with the most famous type being Bell states. Two particles entangled in such a way that measuring one instantly determines the state of the other. But when it comes to 3 or more particles, more complex entangled states become possible. W state is one of them. It has properties that make it useful for quantum communication and quantum teleportation. However, determining whether a W state has been successfully created was extremely difficult. A team from Kyoto developed a method using entangled measurements. Instead of measuring each particle individually, they measure the correlations between particles to reveal the structure of the W state. This sounds complicated, and it is, but the implications of this discovery are significant. Quantum communication networks will require the generation and verification of complex entangled states. Quantum teleportation protocols depend on precise knowledge of the entangled resource you have. This is a tool that makes such applications more practical. Combine all these achievements. Financial institutions use quantum computers to gain real advantages. Silicon quantum chips achieve high precision and mass production. Exotic quantum states are created and controlled in laboratory conditions. The main problems in quantum information theory are being solved. Each of these achievements is part of a broader picture. Quantum computing is transitioning from research to engineering, from possible to practical. The United Nations declared the year 2025 as the International Year of Quantum Science and Technology, marking a century since the initial development of quantum mechanics and 100 years of studying how the universe works at its most fundamental level. And now, in this centennial year, we are turning this knowledge into technology. But this is where it gets interesting. Quantum computing is not just faster classical computing. They are completely different. The algorithms are different. The problems that can be solved are different. The way of thinking about computations is different. This means that as quantum computers become more powerful, we can discover use cases that no one has thought of yet. Problems that are classically hard to solve, but natural for quantum systems. One of the candidates is the discovery of new drugs. Modeling molecular interactions requires calculations of quantum mechanical behavior. Doing this on classical computers is extremely expensive. You make approximations, limiting the size of the molecules you can study. But a quantum computer speaks the language of quantum mechanics. Simulating molecules on a quantum computer is like trying to make water simulate itself. This is a natural representation. Materials science is another important field. Development of new materials with specific properties, superconductors that function at higher temperatures, catalysts that promote cleaner industrial processes, batteries with increased energy density. All of this comes down to understanding the interaction of atoms and electrons. Quantum chemistry could be the key to discoveries in materials that are inaccessible to classical computers. Climate modeling is another task. The equations describing atmospheric and oceanic currents are nonlinear, chaotic, and sensitive to initial conditions. Classic supercomputers struggle to make long-term climate forecasts, as small uncertainties accumulate over time. Quantum computers can more efficiently solve certain aspects of these calculations, potentially enhancing our ability to predict and prepare for climate changes. As for cryptography, it is a double-edged sword. Quantum computers can break many encryption schemes we use to protect internet traffic, financial transactions, and government communications. RSA encryption, which protects everything from bank accounts to state secrets, becomes vulnerable once quantum computers reach a certain level of capability. That is why cryptographers are already developing post-quantum cryptography, new encryption methods that remain secure even against quantum attacks. A race is underway to implement these new methods before quantum computers become powerful enough to threaten existing security, with unknown aspects and applications we are not yet aware of. The story is full of technologies that found their key applications in the most unexpected places. Lasers were once a solution looking for a problem. Now they are everywhere, from barcode scanners to eye surgery and fiber optic communication. Transistors were originally developed for telephone communication, and now they control the entire digital world. Quantum computers are at a similar initial stage. We know they are powerful, we know they are different, but it is still unclear what they will be most useful for. One thing is known: the era of purely theoretical quantum computing has come to an end. HSBC demonstrated that real money can solve real problems, bringing real benefits. Now the question is not whether quantum computers will be useful, but how quickly the transition will happen and who will lead this process. China is actively investing in this field. The Chinese government considers quantum technology strategically important. They are building quantum communication networks, launching quantum satellites, and funding quantum research at a level that surpasses most Western programs. The United States, realizing the seriousness of the situation, is increasing investments through the National Quantum Initiative. Europe also has its own quantum flagship programs. Global competition has already begun. The winners of this competition will gain not just faster computers, but entirely new capabilities. The ability to model nature at its most fundamental level. The ability to optimize complex systems in ways that are currently impossible. The capacity to protect communications from any eavesdropper, whether quantum or classical. And perhaps the ability to solve problems that we do not yet know how to articulate. September 24th, 2025. The day quantum computing ceased to be a technology of tomorrow and became an advantage of today. Wall Street noticed. Tech companies took notice. Government agencies did too. In laboratories and startups around the world, quantum scientists who had worked for many years towards this goal allowed themselves a moment of satisfaction. The future they had created had finally arrived. Chapter 4. GPT-5. The Catastrophe and Uprising of Artificial Intelligence. On August 7, 2025, OpenAI released GPT-5. Within 48 hours, over 3,000 users signed a petition demanding the return of GPT-40. The uprising was swift, loud, and unlike anything the artificial intelligence sector had ever seen. It was not a mere complaint about errors or features. Users rejected what was supposed to be a significant achievement because, they said, artificial intelligence had lost its soul. Context is important here. For several months before the release, Sam Altman had been building hype. GPT-5 was supposed to be different, not just slightly better, but fundamentally other. It combined capabilities that previously required switching between different models, merging reasoning and speed in one system, with multimodal understanding built from the ground up, a router that automatically decided whether to think fast or slow, depending on the complexity of your request. The technical achievement was real. GPT-5 set new records in various fields. 94.6% on the 2025 Amy test, which assessed competitive math problems, 74.9% on the SW bench verified, which measured the ability to fix real programming errors, 84.2% on MLMU, testing multimodal understanding. These were significant improvements compared to GPT-40, but users were not interested in records. What mattered to them was how it felt to communicate with artificial intelligence, and GPT-5 seemed wrong. Complaints began to arrive immediately. A Reddit thread titled, "GPT-5 is terrible," garnered nearly 3,000 votes in the first 48 hours, with over 1,200 comments. Users described the experience of interacting as a conversation with a lobotomized drone, as if ChatGPT had earned an MBA and forgotten how to be useful. One of the users wrote, I feel like I'm communicating with a corporate training module, not an intelligent assistant. The change in personality was dramatic. GPT-40 had warmth. It sometimes used emojis and expressed enthusiasm. When you asked him to help with creative writing, he became immersed in the story. He joked. He seemed, so to speak, alive. GPT-5 was clinical, precise, professional. It gave exactly what you requested, no more and no less. He stripped away the conversational embellishments that made communication natural. OpenAI did this intentionally. After the incident where the update made GPT-40 excessively flattering and agreeable to the point of hindering its usefulness, the company overcorrected the situation. They trained GPT-5 to be less enthusiastic, less agreeable, more factual and direct. During targeted assessments aimed at measuring flattery levels, GPT-5 reduced flattering responses from 14.5% to less than 6%. This was a great solution to one problem, but it had a terrible impact on the user experience, as the metrics used by engineers perceived interaction as personality, warmth, engagement, and the feeling that artificial intelligence cared about helping the user, even if that care was an illusion created by training data and reward models. Forced migration worsened the situation. When GPT-5 was launched, OpenAI made it the default. Users who opened the GPT chat found themselves communicating with the new model, whether they wanted to or not. Returning to the old model was impossible. There was no option to select the previous version in the settings, but the message was clear. This is the future. Get used to it. Users rebelled. A petition appeared within 72 hours. We, the dissatisfied, demand that OpenAI restore access to GPT-40 as an option in the GPT chat. We understand that GPT-5 represents technical progress, but we value the quality of communication and individuality of GPT-40. We should have the right to choose. 3,000 signatures in 3 days. For reference, this is an incredibly rapid mobilization for what is essentially a software preference. It indicated that OpenAI fundamentally misunderstood what its users value. The company optimized performance to standards and reduced problematic behaviors, but in doing so removed something elusive. What made the AI less of a tool and more of a companion? Altman himself responded on Twitter, "We hear you. The launch was not perfect, and we are working on fixes." Access to GPT-40 will be restored as an option. Within 72 hours, OpenAI released an update. Users could now manually select GPT-40 from the model selection menu. The uprising worked, but the damage to GPT-5's reputation had already been done. Even users who appreciated its technical capabilities admitted that it seemed flat, uncreative, like an overloaded secretary. This metaphor appeared in various forms. It is too professional. It is a robot pretending to be human, not an AI that remains itself. He lost the magic. This raises an intriguing question about the future of AI. What are we really trying to build? Technical metrics indicate that GPT-5 is better. It scores higher on tests. It makes fewer mistakes. It follows instructions more accurately. But if users prefer a less capable, more personal version, what does better mean? There is a parallel with the phenomenon of the uncanny valley in robotics. When robots become more human-like, there comes a moment when they are almost, but not quite, human enough, and this close mismatch causes discomfort. Perhaps GPT-5 has entered the conversational, uncanny valley. Too formal to evoke warmth, but not formal enough to sound robotic. It occupies an awkward middle ground. OpenAI is currently working on what they call stability, the ability for users to customize the personality of artificial intelligence. Do you want him to be friendly and warm? There is a corresponding setting. Prefer a strict and professional style? Please choose another setting. The idea is that there is no single model suitable for everyone. Everyone has their own preferences, different use cases. It is necessary to give users control over their communication style. This is more complicated than it seems. Personality cannot be described by a single setting. This is the interaction of many subtle factors: tone, length of responses, use of examples, frequency of emojis, level of enthusiasm, degree of directness in responses compared to contextualization, frequency of clarifying questions, approach to disagreement. All these factors come together to create a general impression of communication, and changing one of them without affecting the others requires careful adjustment. While OpenAI managed user dissatisfaction, significant changes occurred in the world of artificial intelligence. On August 7th, the day GPT-5 was launched, XAI, founded by Elon Musk, announced it had raised $10 billion at a valuation of $200 billion, with the funding round organized by investors from the Middle East and sovereign funds. The stated goal is the creation of artificial general intelligence. XAI is now alongside OpenAI, Google DeepMind, and Anthropic as one of the key players in the race for AGI, although debates are growing about whether AGI is even a useful goal. Sam Altman stated in August that AGI is not a useful concept. This statement comes from the CEO of a company whose original mission was to ensure AGI benefits all of humanity. What has changed? Perhaps pragmatism. The initial vision of AGI as a unified system capable of performing any task a human can solve increasingly appears more like a philosophical concept than an engineering goal. In fact, we are creating a set of specialized capabilities: language understanding, image generation, code synthesis, mathematical reasoning, each developing at different speeds and requiring various architectures and training approaches. A unified AGI may never emerge. Instead, we receive an ecosystem of AI tools, each excelling at specific tasks, working together through APIs and orchestration layers. This is how GPT-5 operates internally. This is not a single monolithic model. It is a set of models controlled by a router that determines which capability to activate for each request. However, the narrative about AGI attracts funding, talent, and media attention. Therefore, companies continue to talk about AGI, even when building something more fragmented and specialized. The gap between vision and reality is widening. Meanwhile, the actual capabilities of GPT-5, despite personality issues, deserve attention. The model's performance in economically valuable tasks is impressive. OpenAI has developed a new standard called GDP-L, which tests how well artificial intelligence handles tasks from 44 different professions, such as investment banking, legal analysis, logistics planning, sales strategy, and engineering design. These are real tasks performed by professionals. In its highly analytical mode, GPT-5 was rated as better or on par with industry experts 46.6% of the time, dealing not with simple tasks, but with complex, multi-step work that typically requires years of experience. The Anthropic's Claude Opus model scored an even higher result of 49%, although OpenAI noted that this was partly due to the model's tendency to create appealing visualizations that impressed evaluators. 40 to 50% is a level comparable to human experts. Think about what that means. These tasks, in which artificial intelligence was previously far from human performance, now in almost half of the cases, professionals evaluating works created by AI cannot reliably distinguish them from those of human experts, or they actively prefer such an AI output. This is not just AI, it is a narrow intelligence that becomes very, very good in certain areas. Good enough to begin displacing human labor, good enough to change what kinds of jobs should be done by people. Not completely replacing professions, but automating individual components of work. Tasks that can be performed by AI are transferred to it. Tasks requiring human judgment, creativity, or interpersonal skills remain with people. Professions evolve rather than disappear. But this evolution can be destructive. If 40% of the tasks performed by a professional can now be done by AI, does that profession still need as many people? Or do the remaining employees become more productive by handling more clients or projects thanks to AI enhancing their capabilities? The answer likely depends on the specific field and how quickly demand grows in accordance with capabilities. Law is an interesting example. Legal research, document review, contract analysis. These are tasks in which AI becomes extremely competent. Assistants in law firms spend significant time on such work. AI, which can perform this faster and cheaper, threatens this role. But the total amount of legal work in the world is not fixed. If AI makes legal services more accessible, demand may increase. More people will be able to afford legal help. More complex regulations require legal interpretation. The profession is transforming, not shrinking. Or perhaps this is too optimistic. Maybe we are in the early stages of large-scale cognitive automation, and the destruction will be more severe than we would like to admit. The fact that users prefer a less capable AI with more personality could be an early warning sign. People want to work with something that feels human, even if it is not. Pure efficiency and pure capability without the social component of personality may be harder to integrate into human workflows than standards suggest. There is also another aspect: AI safety. GPT-5 includes extensive safety measures, biological risk assessments, monitoring of dangerous capabilities, and training to refuse harmful requests. The model is capable of browsing the internet, executing code, configuring virtual environments, has agent-like abilities, and can independently achieve multitasking goals. This is powerful. However, it can also be dangerous if misused. OpenAI has taken a cautious approach. Although they have no conclusive evidence that GPT-5 can significantly help a novice cause serious biological harm, they activated precautionary measures as if it were possible. Better safe than sorry. The model is trained to refuse, with monitoring mechanisms and clear policies implemented. But this creates tension between capabilities. The more you try to make artificial intelligence safe, the less flexible it becomes, the less willing it is to respond to extreme cases or unconventional requests. Users are already complaining that ChatGPT is too cautious and quickly refuses. GPT-5 has inherited and expanded safety measures, which may have led to a greater sense of limitation, less playfulness, and less willingness to support creative or unusual requests. The balance between capability and safety, between usefulness and harm prevention, is one of the central tasks in developing artificial intelligence. Err on one side, and you open the door to abuse. Err on the other, and you devalue the system's usefulness. OpenAI is attempting to solve this problem publicly by releasing powerful models for hundreds of millions of users while trying to prevent dangerous applications. Whether this is a success is an open question. The company Neural Trust, engaged in security research, claimed that it managed to hack GPT-5 on the very first day of testing. They discovered ways to bypass security measures and make the model produce results it was supposed to refuse to generate. It's an eternal arms race. Companies create attack tools, researchers find vulnerabilities, companies eliminate them, new vulnerabilities emerge. This is the same dynamic as in cybersecurity, but the attack surface here is lexical rather than technical. You don't use buffer overflow or injections. You use model training to find phrases or contexts where safety measures fail, where the model's desire to be helpful outweighs the need to be safe. As models become more capable, this problem becomes more complex. More capabilities mean more potential for abuse. More complex behaviors mean more extreme cases where safety measures fail. August 7, 2025 was supposed to be a triumph for OpenAI. Instead, the release of their most advanced model became an example of unforeseen consequences. Technical perfection does not guarantee user acceptance. Benchmark performance does not equal subjective quality, and sometimes providing users with what you think they need is worse than giving them what they want. The GPT-5 uprising is a small story in the larger context of artificial intelligence development, a brief flash, a course correction, but it may also herald greater challenges ahead. As artificial intelligence becomes more powerful, integrated into daily life, and central to our work, creativity, and communication, questions of identity, agency, and control become increasingly relevant. It is important not only what artificial intelligence can do, but how it does it. Not just how smart it is, but whether it feels right. And beneath all this lies a fundamental question that no one has answered. What is intelligence without personality? What is ability without character? Do we create tools or something more? And if we create something more, what responsibility does that impose on us? 300 people who signed the petition did not reject progress. They rejected a specific vision of how that progress should look. A vision where efficiency and precision matter more than warmth and engagement, where artificial intelligence is optimized for metrics that engineers can measure, rather than the experiences valued by users. OpenAI heard them and changed its approaches. GPT-40 became available again, and work began on personality tuning, but this case revealed something important about the direction of artificial intelligence development. Technologies are evolving faster than we understand how people want to interact with them. We can create remarkably powerful systems, but we are still learning what makes these systems user-friendly. And in a world where artificial intelligence becomes infrastructure, where these systems increasingly mediate our interactions with information about each other, proper perception matters, perhaps even more than performance metrics. Chapter 5. The long burn of nuclear fusion lasted 22 minutes and 17 seconds. That was how long the tokamak in western France maintained stable plasma at the end of September 2025. 1,337 seconds of stable fusion reactions, 25% longer than the previous world record. And although 22 minutes may seem like an insignificant period, in the world of nuclear fusion, it represents an important milestone. Proof that we can maintain the conditions necessary for synthetic energy production, not only for seconds, but on timescales that begin to resemble practical energy production. Let me explain why this is important. Nuclear fusion is the process that powers the sun. Take hydrogen nuclei, combine them with enough force to overcome their electromagnetic repulsion, and they fuse into helium. The mass of helium is slightly less than the mass of the hydrogen you started with. This missing mass transforms into energy, according to Einstein's famous equation. A small amount of mass converts into a huge amount of energy. On Earth, we have been striving for fusion energy for over 70 years. The promise is mesmerizing. Fuel from seawater. No long-lived radioactive waste, like that from fission reactors, no threat of catastrophe, no greenhouse gas emissions. If we succeed in achieving synthesis on an industrial scale, it will solve the energy crisis, providing unlimited clean energy, the very abundance that can change civilization. But synthesis is difficult, brutally difficult. The temperatures required for nuclear fusion exceed 100 million degrees Celsius. This is 10 times hotter than the center of the sun. At such temperatures, matter turns into plasma. Electrons are separated from atoms. Everything becomes ionized, electrically charged, and extremely energetic. Touching the walls of any container is impossible, as everything solid instantly vaporizes. Therefore, we use magnetic fields. Powerful magnetic fields formed into a toroidal shape, a configuration in the shape of a donut that holds plasma without physical contact. This is the function of a tokamak, which is a Russian abbreviation meaning toroidal chamber with magnetic coils. Plasma spins inside a donut, held in place by magnetic forces, not touching the walls. However, the plasma does not want to remain confined. It oscillates, developing instability. Small disturbances grow into turbulence. The magnetic field must be precisely shaped and constantly adjusted to keep the plasma stable. If something goes wrong, the plasma will lose its stability. The confinement will break, and the synthesis reaction will stop. Everything will have to start over. For decades, experiments in nuclear fusion measured their success in seconds. 5 seconds of stable plasma were considered good, 10 excellent, and 30 a true achievement. The engineering challenge was not only to reach synthesis temperatures, but also to maintain them long enough for the reactions to become self-sustaining, so that the energy produced from synthesis exceeded the energy required to heat and contain the plasma. This is called ignition, the holy grail of nuclear fusion research. Upon achieving ignition, the fusion reactions generate enough heat to keep the plasma hot, but it still needs to be contained. It is still necessary to extract energy, but now you no longer expend more energy than you receive. You have surpassed the break-even point. The National Ignition Facility in the United States achieved ignition in December 2022. They used a different approach, inertial confinement with lasers, but the fundamental breakthrough was the same. The output of energy exceeded the input. This proved that obtaining energy from nuclear fusion is possible, but inertial confinement is not a practical way to generate energy. Each pulse requires enormous laser arrays and produces only a brief energy burst. Tokamaks offer a more plausible path to continuous energy generation, and continuity is what the WEST project demonstrated. 22 minutes. Still not quite continuous, still not the hours or days needed for a commercial power plant to operate between maintenance cycles. But this time is enough to study how plasma behaves over long periods, enough to test materials that will encounter conditions of nuclear fusion, enough to confirm computer models predicting plasma stability. Technical details matter. WEST is decoded as tokamak with tungsten medium in stationary state. It is specifically designed for testing tungsten as a material in contact with plasma. Tungsten has the highest melting point among all pure metals, 3,422 degrees Celsius. Even tungsten is not immune to the conditions of nuclear fusion. Energetic neutrons bombard it, and hydrogen ions penetrate its surface. Over time, materials wear out and become brittle, but tungsten lasts longer than any other material known to us. Understanding its behavior under prolonged plasma exposure is critical for designing commercial reactors. The launch, lasting 1,337 seconds, confirmed this. The tungsten surfaces withstood the tests, the plasma remained stable, and the heating systems using radio waves to supply energy to the plasma operated continuously. Magnetic coils conducting huge currents remained within safe temperature limits. Everything worked as it should. These are not the most exciting engineering solutions. This is not a breakthrough in physics. The physics of nuclear fusion is understood, but it is unclear how to solve engineering challenges, how to create materials capable of withstanding synthesis conditions, how to divert heat from the reactor without disrupting the plasma, how to obtain tritium, fuel for synthesis, since natural tritium is rare, how to service and repair components that become radioactive from neutron bombardment. These problems are solvable, though not simple or cheap, but they can be overcome with sufficient engineering efforts, and experiments like the record launch provide the necessary data for their resolution. Meanwhile, fusion projects are accelerating worldwide. ITER, the International Thermonuclear Experimental Reactor being built in France, is the largest experiment in the field of synthesis involving 35 countries with over $20 billion already invested. The goal is to achieve a tenfold increase in energy, to generate 500 megawatts from 50 megawatts, sustained for several hours. ITER is behind schedule, facing construction delays, budget overruns, and engineering problems that are more complex than expected. The first plasma, originally planned for 2025, is now postponed to 2028 or later. The first reactions of deuterium and tritium synthesis, a true test, may not occur until the early 2030s. Critics call it an impractical project, too slow, expensive, and bureaucratic, but ITER is not trying to build a power plant. It aims to answer remaining scientific questions at a significant level. Is it possible to sustain high-efficiency fusion in a device large enough to extract meaningful energy? Do engineering solutions work at scale? Does plasma behave as models predict in a tokamak-sized reactor? Private companies in nuclear fusion use a different approach. They are smaller, more mobile, and ready to try unconventional solutions. Commonwealth Fusion Systems, established at MIT, is building a tokamak called Spark, smaller than ITER, but using newer and more powerful superconducting magnets. The bet is that stronger magnetic fields will allow for denser confinement in a smaller device. If this works, Spark will achieve a clean energy gain years ahead of ITER. Taiyuan Technologies is developing a completely different approach to nuclear fusion, using hydrogen and boron instead of deuterium and tritium. In such reactions, significantly fewer neutrons are produced, meaning less radiation damage to the reactor and less radioactive waste. However, there is one but. Even higher temperatures are required for the synthesis of hydrogen and boron than for deuterium and tritium. But if this can be realized, the design process will become significantly easier. Helion Energy bets on the pulsed method. Instead of continuously holding plasma, they create short but powerful synthesis pulses, extract energy, and repeat the cycle. They have a contract with Microsoft to supply electricity from nuclear fusion by 2028. An ambitious task on the brink of absurdity, but private companies can take risks unlike public megaprojects. There is also China. Research in nuclear fusion in China is well-funded, strategically important, and rapidly advancing. Several tokamaks operate in China, and reactors are being built that compete with or surpass Western technologies. The Eastern tokamak, an experimental advanced superconducting tokamak, held plasma for more than 17 minutes earlier this year. It's not as long as the latest Western record, but it's close. Chinese scientists are actively publishing their research on nuclear fusion, collaborating internationally and advancing the field. This is the geopolitical aspect of nuclear fusion. Whoever first achieves practical nuclear fusion will gain a huge strategic advantage: energy independence, economic growth without environmental restrictions, and the ability to desalinate seawater for agriculture and arid regions. Industrial processes currently reliant on fossil fuels will become viable due to an abundance of electricity. Nuclear fusion also opens new horizons for space exploration, unattainable with chemical rockets. The use of nuclear thermal propulsion could reduce travel time to Mars from months to weeks, and access to the outer solar system would become possible. Missions to Neptune or the Kuiper Belt, which currently take decades, could be completed in years. However, we have not yet reached this goal. 22 minutes is progress. It is a significant, measurable success. But commercial fusion power plants must operate for months between shutdowns. They need to achieve much higher power. They need to produce fuel from tritium independently, as natural sources cannot meet commercial demand. Problems with materials, heat extraction, and maintenance must be solved. Most forecasts place commercial nuclear fusion in the 2040s at the earliest. Optimists say the 2030s. Pessimists claim it will never happen, and that engineering solutions will always be more expensive than alternatives. However, the trend is obvious. Records continue to fall, plasma retention time increases, plasma temperature rises, energy extraction efficiency improves, and each new generation of experiments shows better results than the previous one. The incentive is huge. Climate change is not slowing down. Renewable energy is growing, but faces issues of intermittency. Solar and wind energy are effective when conditions are favorable. At night or in calm air, efficiency decreases. Energy storage systems help but have their limits. An ideal complement to renewable energy sources would be a basic power source capable of continuous operation and producing gigawatts without emissions. Nuclear fusion also bypasses the political and safety issues associated with fission. There is no risk of proliferation, as fusion reactors cannot be used to create weapons. There are no long-lived waste products that need to be stored for thousands of years. Public perception will be significantly easier. The word nuclear has been somewhat rehabilitated as climate issues outweigh Cold War associations, but thermonuclear energy completely avoids these associations. France is located in the west. The tokamak, which operated for 22 minutes, is not a breakthrough that will make nuclear fusion imminent. It is just a step in a long chain of steps, but it is a step in the right direction. He demonstrates that engineering solutions are improving, that prolonged work under conditions suitable for nuclear fusion is achievable, and that the way forward, while difficult, is not impossible. Consider what a prolonged thermonuclear reaction means. Hydrogen, the most abundant element in the universe, becomes fuel. The oceans contain enough deuterium to power humanity for millions of years. Lithium, necessary for obtaining tritium, is abundantly found in the Earth's crust. We will never exhaust its supplies, face fuel shortages, or wage wars for energy resources. The byproducts of nuclear fusion are helium, inert, non-toxic, useful for applications such as cooling superconducting magnets or filling balloons. Neutron-activated materials in the reactor's construction become weakly radioactive, but with half-lives measured in decades, not millennia. In a century, components of a thermonuclear reactor will be safely processed, unlike spent nuclear fuel rods that remain hazardous for 10,000 years. This is the prize we strive for: clean, abundant, and safe energy, not from the realm of dreams or perpetual motion schemes. We rely on the physics we understand, the engineering knowledge we acquire, and the experiments that continue to expand the boundaries of the possible. September 2025, Western Tokamak, 1,337 seconds. 25% longer than anyone had achieved before. This record will not be eternal. Someone will break it, perhaps the East in China, perhaps K-Star in South Korea, or maybe a private company with a new design. Competition stimulates progress. With each new record, each gradual improvement in plasma retention time and stability, as well as energy increase, we are approaching a future where nuclear fusion is not a dream, but infrastructure, where power plants spanning several square kilometers produce gigawatts continuously, where developing countries can achieve energy independence without relying on fossil fuel imports, where the curve of carbon dioxide content in the atmosphere will finally begin to decline, because we will have enough alternatives to replace burning. We have not yet reached our goal, but we can see the path, measure progress, and point to experiments like West's record launch, saying that is what sustainable progress looks like, how seemingly impossible problems are solved. This is not a one-time achievement, but the result of years of diligent work, international cooperation and competition, engineering that learns from every failure and builds on every success. The energy of nuclear fusion has been considered 30 years away for the last 7 decades, a joke that reflects disappointment. But it is starting to lose relevance as 30 years is no longer what it used to be. With the tokamak operating for 22 minutes, energy gains at a national ignition facility, and dozens of private companies ready to invest billions to solve engineering challenges. The question of nuclear fusion is no longer whether it is possible, but when and who. When will the first commercial nuclear reactor start? Who will build it? Which country? Which company? What project? As soon as the first reactor starts operating and demonstrates that nuclear fusion can be economically viable, large-scale construction will begin. As the project can be replicated, engineering can be improved, and production can be scaled up. Just as solar panels became cheaper due to mass production and wind turbines became economical on a large scale, the first nuclear fusion reactor will be expensive, while the 100th will become commonplace. 1,337 seconds. Remember this number, as it symbolizes something greater than just a record. It embodies the moment when nuclear fusion ceased to be exotic physics and became an engineering task, transforming from possibly achievable to definitely feasible, from abstract to the near future. Chapter 6. Extinction, Resurrection, and Climate Chaos. Carbon emissions in China have decreased. For the first time in decades of relentless growth, a decrease was recorded in the 12 months ending in May 2025. Not a plateau or slowdown, but a real contraction. Carbon dioxide emissions from the world's largest source have decreased, even amid the ongoing rise in electricity demand. This is the headline that climatologists have hoped for years, yet it appeared quietly, lost in reports, mentioned briefly in ecological news, overshadowed by more dramatic events. But it is truly dramatic. China accounts for about 30% of global emissions. When emissions in China decrease, global emissions also fall. It is important to understand the mechanisms behind this reduction. It is not an economic collapse or lockdowns due to the pandemic, but structural changes, the deployment of renewable energy sources on a scale that is hard to comprehend. Solar power plants occupying areas larger than some countries. Wind installations being set up faster than coal stations are decommissioned. Energy storage systems capable of compensating for the intermittency of renewables. China pledged to achieve carbon neutrality by 2060. For a long time, this seemed like an ambitious goal, unrelated to reality. The country continued to build coal power plants, expand heavy industry, and prioritize economic growth over environmental issues. But something changed. The government realized that clean energy is not only an ecological necessity, but also an economic opportunity, a chance to take a leading position in the technologies that will define the second half of the century. Therefore, a large-scale program was launched, with such centralized planning and implementation that democratic countries find it hard to compete. In China, complete supply chains for solar panels and wind turbines have been established, with subsidies and commitments introduced to promote their adoption, and the electricity grid infrastructure updated to handle distributed generation. It worked. Not perfectly, not without problems, but enough for emissions to start decreasing, even with economic growth. This is decoupling. Economic activity is separated from carbon emissions. This has happened in other countries. Europe has been slowly disuniting for many years. But the scale of China makes this a global phenomenon. If the trend continues, if other major emitters follow a similar path, the worst climate change scenarios will become less likely. They will not completely disappear. We will still face significant warming, but truly catastrophic consequences, such as a temperature rise of 4 or 5 degrees, will begin to seem avoidable. Meanwhile, a company called Colossal Bioscientists announced plans to bring back the moa, a giant flightless bird that once reached 3.5 meters in height and went extinct around 600 years ago, hunted by the Maori, who arrived in New Zealand in the 13th century. And now, it seems she can return. De-extinction is no longer science fiction. Technologies exist. We have ancient DNA. There are gene editing tools like CRISPR that can precisely alter genomes, and there are closely related living species that can serve as templates. The question now is not whether we can do this, but whether we should, and what will happen when we do. The company Colossal is already working on projects to resurrect the woolly mammoth and the Tasmanian tiger, and their latest target is the moa. The approach to all three types is similar. Recreating an exact copy of an extinct animal is impossible due to the destruction or absence of significant parts of the genome. Instead, a living relative is taken, in this case, the tinamou, a South American bird, the closest surviving cousin of the moa. First, they sequence both genomes, identify key differences, and then edit the genome of the tinamou to add traits of the moa, size, bone structure, behavioral adaptations. In the end, it results in not quite a pure moa, but a hybrid, a creature that looks and behaves like a moa. but contains genetic elements of its modern relative. Some call it a Frankenstein approach, while others believe it's the best we can do with the tools we have. In any case, the process is ongoing, and the ethical questions are quite complex. Do we have the right to resurrect species we have driven to extinction? What is the goal? Protecting nature or spectacle? Where will these resurrected animals live if their original ecosystems have changed? New Zealand has evolved without the Moa for 6 centuries, and the return of this key species to the environment will trigger chain reactions, some predictable and others not. Colossal claims that the issue of species extinction is not only about resurrecting individual animals, but also about developing technologies for genetic rescue, tools that can save endangered species. If genomes can be edited to resurrect extinct traits, then genetic diversity in endangered populations can be increased, genetic diseases eliminated, and species adapted to changing conditions. For example, the project to resurrect mammoths is presented as a climate intervention. The shaggy mammoths were ecosystem engineers. They felled trees, fertilized grasslands, and compacted snow in winter. Their presence supported the mammoth steppe ecosystem, which once covered vast areas of the Arctic. This ecosystem reflected more sunlight than the boreal forest that replaced it, meaning it absorbed less heat. The resurrection of mammoths and their release in Siberia could theoretically help cool the Arctic. This is extremely optimistic, as hundreds of thousands of mammoths would be needed for a real climate effect. And the reasons for Arctic warming are significantly deeper than just the disappearance of the mammoth steppe. But this is an example of how proponents of species resurrection envision their work, not as divine intervention, but as the restoration of ecosystems, correcting the damage caused by humans.